Okay, let's give you guys some more practice. So similar to the previous video, we've got the same surface. But this time, instead of the constraint being a straight line, our constraint this time is a circle of radius 2. So our constraint is a circle of radius 2, and your job is to find the maximum and the minimum value of this function given this constraint. So you can think of this constraint as being the domain. You can think of it as being your domain. You can only live on this blue line, and your job is to find the maximum value of this function and the minimum value of this function, and you have to live on this blue line. Okay, so press pause and have a go. Okay, so to do this, let's turn this function into let's turn this into a function of two variables. So turn this into a function of two variables. So that will then give us this thing here. So now we can take the gradient. We can find the gradient vector of both functions. So the gradient vector for this function is given by this. The gradient vector for this function is given by this. So let me illustrate that on Desmos. So we've got our gradient vector. So for the So for the function itself, this is our gradient vector. Same as in the previous video, the gradient vector would be the same, but this time our gradient vector would be like this for the blue circle. So our job is to find a point where hang on, let me just elaborate on this bit here. Let me just jump back to here. So remember, the vertex of our function is somewhere is at 0, is at 1, 1. So in between 1 and this level here, we've got millions of circles here like this, and we're trying to find a point where there exists a point. Hang on. There exists a point somewhere. So you've got lots of circles like this. Hang on. So the gradient vector for the red circle for our surface will look something like this, and then the gradient vector for our domain, our constraint, is also, it could be pointing this direction or it could be pointing this direction, but we're basically looking for this point here where the two gradient vectors differ by a scalar amount. I think there's another one over here somewhere, because if you extend our level curves, so you've got another one here, a bigger one over here, and a bigger one over here. So there exists another point here where the two gradient vectors will differ by a scalar amount. So we are looking for this point and this point. So let me jump back to Desmos. So you can see that somewhere around here, the two gradient vectors differ by well, they're pointing the same direction in effect, or it could be a negative direction. And there's another one over here somewhere. So if I drag this across here, hang on, you can see that they are pointing the same direction. There's a point somewhere where they differ by a scalar amount. Okay, so our job is to well, those points occur when this gradient vector differs from this gradient vector by a scalar amount. So basically we can put this into here, that will then give us this, and we can put this into here, that will then give us this thing here, and we've got our lambda. So so that will then take us to here. So when you get to here, it's really a case of you finding x, y, meaning the position on our xy plane, and lambda in such a way that this side equals this side. So do whatever you have to do in order to find x, y, and lambda in such a way that this thing is the same as this thing. Well, you demanding that this thing is the same as this thing is the same as you demanding that this thing is the same as this thing. Because if you look at the I component, the two I components must be the same, meaning this must be the same as this. And then if you look at the j component, this component must be the same as this, so you can say that this must equal this. So you trying to satisfy this is the same as you trying to satisfy these two. So do whatever you have to do, eliminate x, y, or lambda. In this case it's easy to eliminate lambda. So let's divide both sides by x. So divide both sides by x, and then looking at this, divide both sides by y. So 2 lambda, 2 lambda. So this must equal this. So you demanding these two to be true is the same as you demanding this to be true. So now times both sides by x, times both sides by y. That will then take us to here. That will then take us to here. These two cancel each other out. Divide both sides by -2. So y must be the same as x, meaning y equals x looks like this. And don't forget, we have to live on the blue circle. So we are looking for this point and this point. Just remember, y must be the same as x. Well, if y must be the same as x, let's look back at our constraint. So looking at our constraint is when it spits out a value of 0. So this is our constraint here. So we know that y must be the same as x. Eliminate something here. Let's eliminate y. So put this into here. That will then take us to here. So x must be plus or -2. Well, if x must be plus or -2, then y must be plus or -2 because of this. So we know x and y. So we know x and y. X and y. When it's so hang on, going back to here, y equals x would be this diagonal line. So this point here must be √2 comma √2. This point here must be √2 comma -√2 comma -√2. So this could be our highest point, or it could be our lowest point. We just don't know yet. Well, you might have a gut instinct. This could be our highest point or our lowest point. Let's pretend we didn't know. We don't know, so let's put it into the function. When you put it into the function, when you put √2 and √2 into the function, this whole thing here will then become this. And then when you put -2 and -2 into the function, it then becomes this. So this is our max, and this must be our min. So going back to here, this is our surface here. The red, all the red circles represents our surface. Well, the highest point on that surface is this point here at -2 √2 and -√2, and the lowest point occurs when it's is at √2 comma √2. Okay, and the elevations would be this and this. Okay.